In the silence between stars, something moves with purpose, and perhaps, just perhaps, it carries not destruction, but the universe's oldest song. Welcome to Sleepy Cosmos, where we drift through the mysteries that keep scientists awake at night. There is an object moving through our solar system right now, a visitor from depth so profound that the human mind struggles to comprehend the distances involved. And it moves with a grace that suggests something more than random chance, something that whispers of intention without speaking, of meaning without words. And its name is 3I divided by Atlas, the third interstellar object we have ever detected crossing through our cosmic neighborhood, though surely countless others have passed unseen through the long night of human history. Through epochs, when no one looked up with instruments sensitive enough to catch their fleeting shadows against the infinite dark. This object, discovered in the early autumn of 2024, arrived not with the blazing drama of a catastrophic impact, but with the quiet dignity of a messenger arriving at a long-appointed meeting. And perhaps that is precisely what it is. Not a harbinger of endings, but a carrier of patterns, a vessel of cosmic mathematics traveling across the light years, with information encoded in its very structure, in the way it reflects sunlight, in the composition of its surface, in the elegant arc of its trajectory through space. Consider for a moment what it means to be interstellar, to have originated not in the familiar precincts of our sun's domain, but in another system entirely, orbiting another star, perhaps bathed in different wavelengths of light, shaped by different gravitational forces, composed of materials that condense from a molecular cloud with a unique chemical signature, and then to be cast loose, ejected by some gravitational interaction or stellar event into the vast emptiness between the stars, traveling for millennia or perhaps millions of years through the cold and dark, through regions of space so empty that atoms are separated by distances vast enough to swallow worlds, and yet maintaining coherence, maintaining form, until finally, by chance, or perhaps by something that only resembles chance, entering the sphere of influence of our sun, our small yellow star in an ordinary spiral arm of an ordinary galaxy, and beginning the long fall inward toward the light. The journey of such an object is almost incomprehensible in its duration and its loneliness, and yet 3I divided by Atlas made this journey, surviving whatever crucible birthed it, whatever chaos flung it into the void, and it arrived here, now, in this particular moment, when humanity possesses just enough technology to notice, just enough curiosity to wonder, just enough imagination to ask whether its arrival might mean something more than accident. The story of interstellar objects begins, in our awareness at least, with Oumuamua, that strange, elongated visitor that appeared in October of 2017 and puzzled astronomers with its unusual shape and its unexpected acceleration as it departed the inner solar system, moving in ways that suggested outgassing like a comet, but without the visible coma of vaporizing ice that comets typically display. And immediately the speculation began. The careful scientific hypotheses alongside the more romantic possibilities. Could it be artificial? Could it be a probe? Could it be a light sail pushed by radiation pressure? And while most scientists settled on natural explanations involving exotic ices or unusual structural properties, the very fact that such questions could be seriously discussed revealed something important about humanity's readiness to encounter the truly alien, the truly other, and Oumuamua vanished back into the dark before we could study it properly, before we could send a probe to intercept it, before we could answer the questions it raised, leaving behind only data points and speculation and a renewed attention to the sky, a heightened awareness that our solar system is not isolated but permeable, visited by wanderers from other stellar neighborhoods, and that we should watch more carefully for what else might arrive. Then came 2I divided by Borisov, discovered in August of 2019 by amateur astronomer Gennady Borisov, and this visitor was more conventional in many ways, clearly a comet with a visible coma and tail. outgassing as it approached the sun, behaving in ways that matched our models and expectations, and yet it too was profoundly exotic in its chemistry. Analysis revealing carbon monoxide concentrations much higher than typical solar system comets, suggesting formation in a much colder environment, perhaps in the outer reaches of another star system. And it reminded us that even when interstellar visitors follow familiar patterns, they carry with them the signatures of alien environments, the chemical fingerprints of other stellar nurseries, other protoplanetary disks, other conditions of formation. And studying 2I divided by Borisov was like reading a message written in familiar letters, but describing places we have never seen, temperatures we have never measured, pressures and densities that exist nowhere in our experience except as abstractions in equations and computer models. And now 3I divided by Atlas has arrived, detected by the Asteroid Terrestrial Impact Last Alert System, the Atlas survey that constantly monitors the sky for objects that might pose a threat to Earth. Though this visitor, following its hyperbolic trajectory, will pass through and depart without coming dangerously close to our planet, and initial observations suggest something remarkable, something that has caused a quiet excitement among those who study such things. Because 3I divided by Atlas appears to exhibit properties that are neither pure asteroidal nor purely cometary, but something in between, or perhaps something entirely its own. And more intriguing still are the patterns emerging from spectroscopic analysis, the way it reflects and absorbs light in ratios that seem almost too regular, too structured, as if the surface composition or the internal structure follows principles that natural processes sometimes approach but rarely achieve with such precision. And this is where the story becomes not just interesting but potentially profound, because patterns are the language of meaning. Patterns are how the universe communicates information, how it encodes structure and relationship and law, and when we find patterns in nature, we are finding the deep grammar of existence itself, the mathematical substrate upon which reality is constructed. The Fibonacci sequence is perhaps the most famous example of nature's love affair with mathematical order, that simple progression where each number is the sum of the two preceding ones, 1, 1, 2, 3, 5, 8, 13, 21, and so forth into infinity. And this sequence, discovered or perhaps rediscovered by Leonardo Fibonacci in the 13th century, appears everywhere in the natural world, in the spiral arrangement of seeds in a sunflower head, in the branching of trees, in the spiral shells of mollusks, in the breeding patterns of rabbits, in the proportions of the human body, in the structure of galaxies. And the question that haunts anyone who contemplates this ubiquity is whether these patterns emerge merely from the physics of efficient packing and energy minimization, or whether they represent something deeper, some fundamental aesthetic principle built into the architecture of the cosmos itself, some preference the universe has for certain ratios and relationships, and the golden ratio, phi, approximately 1/618, which is intimately related to the Fibonacci sequence, appears in so many contexts across such vast scales that coincidence begins to strain as an explanation, and we are left wondering whether mathematics is something we invented to describe the universe, or something we discovered that was always already there, woven into the fabric of space and time and matter. When astronomers analyzing the light curves of 3I divided by Atlas, the way its brightness varies as it rotates and travels, began to notice periodicities and ratios that approximated Fibonacci relationships, it could have been dismissed as pareidolia, as the human tendency to find patterns even in randomness, the same cognitive quirk that makes us see faces in clouds and hear voices in white noise. Except that the matches were too close, too consistent across multiple wavelengths of observation, too stable over the weeks of monitoring, and while no serious scientist would claim certainty, while the proper response to anomalous data is always caution and further investigation, there is nonetheless a growing sense that 3I divided by Atlas may be something unprecedented, Not artificial in the sense of being manufactured by intelligent beings, but not entirely random either. Perhaps something that represents a category we have not yet named, a phenomenon that bridges the gap between the purely natural and the purposefully constructed. And if this sounds mystical or unscientific, consider that the boundary between these categories is less clear than we often pretend. Consider that crystals grow in geometric patterns without any guiding intelligence, that soap bubbles minimize surface area according to mathematical principles without knowing calculus, that the universe has been solving optimization problems and generating complex order since long before minds existed to appreciate it. The possibility that 3I divided by Atlas might be carrying information might be what some researchers have quietly begun to call a cosmic messenger. It does not require the existence of alien civilizations deliberately sending messages, though of course that possibility cannot be entirely excluded, and indeed adds a layer of romance to the speculation. But the more subtle and perhaps more profound possibility is that the universe itself generates meaning. That physical processes operating over vast scales of space and time can produce structures that embody information in the same way that sedimentary rocks embody information about ancient climates, the same way that the cosmic microwave background radiation embodies information about the state of the universe 380,000 years after the Big Bang. And if 3I divided by Atlas formed in an environment where certain resonances were present, where certain frequencies of energy and matter interacted in particular ways, it might carry in its structure a record of those conditions, a kind of fossil not of living things but of physical states, of quantum configurations, of field strengths and particle densities. And reading that record could teach us about environments and processes that exist nowhere in our solar system, about the conditions that prevail in other stellar neighborhoods, about the diversity of cosmic environments and the range of possible physical states that matter can assume. Light is the primary way we have of interrogating such objects. Light emitted by the sun and reflected from their surfaces. Light that carries information about composition and texture and structure and spectroscopy. The analysis of light broken into its component wavelengths reveals the chemical signatures of elements and molecules, the absorption lines where specific atoms have taken energy from the passing photons, and this technique has allowed us to determine that 3I divided by Atlas has an unusual abundance of organic compounds, carbon-based molecules of the sort that on Earth are associated with life, but that we know can also form through purely abiotic processes in the cold chemistry of interstellar space, in molecular clouds where dust grains serve as catalytic surfaces for the assembly of increasingly complex molecules. And the presence of these organics does not suggest that 3I divided by Atlas carries life or is itself alive in any meaningful sense, but it does suggest that the building blocks of life, the chemical toolkit that enables biological complexity, is widespread in the universe. And this is both humbling and exhilarating. Humbling because it suggests that the chemistry that made us possible is not special or rare but common and inevitable. Exhilarating because it implies that wherever conditions are right, these building blocks are available, ready to be assembled into systems of increasing complexity, ready to bootstrap themselves towards something that might eventually be called living. But beyond chemistry, there is structure, there is form, there is the question of shape and symmetry, and how these properties relate to the history of an object. And 3I divided by Atlas appears to be tumbling in a complex rotation, not spinning. G, simply around a single axis, but exhibiting what astronomers call non-principal axis rotation, a wobbly tumbling motion that suggests either that it has an irregular shape or that it experienced some significant torque or impact in its past, something that set it spinning in this complicated way, and the periodicity of this tumble, measured in hours and days as it moves through our solar system, shows those curious Fibonacci-like ratios that have drawn attention. The relationship between the primary rotation period and secondary wobble approaching the golden ratio, with a precision that seems unlikely to be coincidental, though of course in a universe as large as ours, Unlikely things happen constantly simply because there are so many opportunities for them to occur. And yet, there is something compelling about the idea that this object, which has traveled so far and for so long, might embody, in its very motion, a mathematical principle that appears again and again throughout nature, as if the universe has preferred modes of being, preferred patterns that emerge at every scale from quantum to cosmic. The ancient peoples who looked up at the night sky with naked eyes, unaided by technology, saw things that we have lost in our light-polluted modern world. They saw the Milky Way as a river of light spanning the heavens. They saw planets wandering among the fixed stars. They saw comets appearing without warning, growing bright and then fading. And these comets were often interpreted as omens, as messages from the gods or harbingers of change. And while we now understand omets as natural objects following Newtonian trajectories, icy bodies from the outer reaches of the solar system perturbed into the inner system, where solar radiation causes them to outgas and develop their characteristic tails, we have perhaps lost something in our mechanical understanding, lost the sense of awe and significance that our ancestors felt, the intuition that something coming from beyond, from the realm of the fixed stars as they understood it, might carry meaning, might represent a kind of communication. And maybe they were not entirely wrong. Maybe they understood on some level that the universe is not mute and dead, but constantly speaking to us in the language of matter and energy, in the patterns of light and gravity, in the motions of celestial bodies. And our task is not to dismiss their sense of cosmic significance, but to translate it into a framework that respects both scientific rigor and the profound strangeness of existence. The Babylonians kept meticulous records of celestial phenomena, tracking the positions of planets and the appearances of comets on clay tablets in cuneiform script, and these records spanned centuries, allowing them to discover periodicities, to predict eclipses and planetary conjunctions, and in doing so, they were engaging in the same fundamental practice that modern astronomers employ, which is the search for patterns, the attempt to find order and regularity in the apparent chaos of the heavens. And this search is driven by an intuition that the universe is lawful, that it follows rules, that past behavior predicts future behavior. And this intuition has proven profoundly productive, has enabled the entire scientific revolution, has allowed us to send probes to other planets and predict the existence of Neptune before it was seen, and verify Einstein's equations through the bending of starlight around the sun. And yet the success of this approach sometimes makes us forget how strange it is, how miraculous that the universe should be comprehensible at all, that mathematics developed by human minds should map so precisely onto physical reality, that equations scratched on paper should predict the behavior of objects billions of light years away. And this unreasonable effectiveness of mathematics, as the physicist Eugene Wigner called it, remains one of the deepest mysteries, perhaps suggesting that mind and matter are not as separate as we imagine, that cognition and cosmos arise from the same underlying principles, that in understanding the universe, we are in some sense the universe understanding itself. When 3I divided by Atlas passes through the plane of the ecliptic, the imaginary flat disk within which most planets orbit, it will do so at an angle that is steep but not perpendicular, coming in from above the plane at roughly 35 degrees, a trajectory that speaks to its interstellar origin, because objects born in our solar system tend to orbit in or near the ecliptic plane, all having condensed from the same protoplanetary disk that swirled around the young sun 4.5 billion years ago. Whereas interstellar visitors come from random directions, from orbits around other stars with other orientations, and the hyperbolic shape of 3I divided by Atlas's trajectory, coming in from infinity and heading back to infinity, unbound by the sun's gravity, is the clear signature of an interstellar origin. And this object will spend only a few months within the inner solar system before departing forever, accelerating as it falls toward the sun, and then slowing as it climbs back out toward the outer darkness. And we have this brief window to study it, to gather data, to analyze its composition and structure, to try to understand what it can tell us about the space between stars, about the nature of matter in other stellar systems, about the processes that create and destroy and transform objects in the cosmic environment. The idea of balance, of harmony, of the universe tending towards certain stable configurations is not just mysticism, but is encoded in physical law, in the way that entropy increases, but local pockets of order can emerge and persist, in the way that gravitational systems settle into orbital resonances, in the way that chemical bonds form when energy is minimized, in the way that ecosystems reach climax states where species populations stabilize in relationship to each other. And perhaps what we call natural selection is just another manifestation of this tendency. Not a random process, but a directed search through possibility space toward configurations that persist, that maintain themselves against the dissolution that entropy demands. And life itself is the ultimate example of this. Organisms maintaining improbable organization through constant expenditure of energy, standing as temporary negations of the second law of thermodynamics, local decreases in entropy, bought at the price of greater entropy elsewhere. And the question that haunts biology is whether this is merely chemistry, merely the inevitable result of certain molecular configurations in certain environments, or whether there is something more, some principle of self-organization, some attractor in the space of possible states toward which matter naturally flows when conditions allow. And if such a principle exists, if there is something we might call a life force without meaning anything supernatural, just meaning a tendency of matter and energy to organize in particular ways, then perhaps this principle operates not just on planets but throughout the universe, in interstellar clouds, in protoplanetary disks, in the accretion flows around black holes, everywhere that energy flows and matter accumulates. And perhaps 3I divided by Atlas, in its small way, is an expression of this principle, a packet of organized matter that has maintained its coherence across interstellar distances, that embodies in its structure some lesson about how the universe prefers to arrange itself. The cosmic microwave background, that faint glow of radiation that fills all of space, the cold remnant of the Big Bang, contains tiny fluctuations, slight differences in temperature from one region to another. And these fluctuations, mapped by satellites like COBE and WMAP and Planck, show patterns that reflect the quantum fluctuations present in the first moments after the Big Bang, fluctuations that were inflated to cosmic scales during the brief period of exponential expansion called inflation, and these patterns became the seeds of all later structure, the slight overdensities that eventually collapsed under gravity to form galaxies and stars and planets. And so everything we see, all the structure in the universe, emerged from quantum randomness amplified to cosmic scale. And yet even in this randomness, there are patterns. The power spectrum of the fluctuations follows specific mathematical forms predicted by models of inflation. And if we could somehow trace back the history of every atom in 3I divided by Atlas, we would find that they too emerged from this process, that they were forged in the cores of stars in some other part of the galaxy, released into space when those stars died, incorporated into a molecular cloud, condensed into a protoplanetary disk, assembled into a planetesimal or comet, and then ejected into interstellar space, carrying with them this long history, this cosmic heritage, and the fact that we can reconstruct this history, that we can read in the composition and isotope ratios of an object, its entire biography stretching back to the early universe, is a kind of magic, a kind of time travel, and it means that every object we study is a messenger from the past, carrying information about conditions and processes that occurred long ago and far away. The silence of space is not really silence, but a cacophony of radiation. Electromagnetic waves at every frequency, from long wavelength radio to high-energy gamma rays. And this radiation carries information, encodes in its intensity and polarization and spectrum the properties of whatever emitted or reflected or scattered it. And astronomical instruments are essentially tools for translating this radiation into forms that human senses and minds can process, into images and graphs and numbers. And through this translation, we have learned that the universe is far stranger than our ancestors imagined, that it contains neutron stars so dense that a teaspoon of their matter would weigh billions of tons, that it contains black holes from which nothing can escape, that it contains dark matter which we cannot see, but which outweighs visible matter by a factor of 5, that it contains dark energy which is causing the expansion of space itself to accelerate, and these discoveries were made not by traveling to distant locations, but by patiently gathering and analyzing light, by building larger telescopes and more sensitive detectors, by developing theories that could explain the patterns in the data, and this process continues. Each new instrument opening new windows on the universe, revealing phenomena that were previously invisible. And it is reasonable to expect that many of our current theories will prove incomplete or incorrect, that future observations will reveal new physics, new phenomena, new mysteries, and perhaps 3I divided by Atlas is an early example of something we will come to recognize as common, a category of object that we have not yet properly named or understood, something that bridges the gap between comet and asteroid, between natural and structured, between random and meaningful. There is a concept in astrobiology called the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface, not too hot and not too cold. And Earth sits comfortably in this zone around our sun, and this is why we have oceans, why we have weather, why we have life. But the concept can be extended beyond just temperature. We can think about a chemical Goldilocks zone, where the right elements are available in the right abundances, about a temporal Goldilocks zone, where the universe is old enough for heavy elements to have been created in stars, but young enough that stars are still forming and energy is available, about a structural Goldilocks zone, where complexity can emerge and persist, and perhaps our existence here and now is the result of falling into multiple overlapping Goldilocks zones, of being in just the right place, at just the right time, with just the right conditions. And this raises the question of how common such coincidences are, whether they are indeed coincidental or whether the universe is in some sense fine-tuned, whether the physical constants that govern reality have the values they do because those are the only values that allow complexity and consciousness to emerge, and this leads to speculations about multiple universes, about the anthropic principle, about the possibility that we live in one of many universes and naturally find ourselves in one where our existence is possible, because we could not exist to observe any other kind. And these ideas push at the boundaries of science, at the line between what can be tested and what is purely philosophical. But they are worth contemplating because they speak to the fundamental question of why there is something rather than nothing, why the universe exists at all, and why it has the particular properties it does. The mathematics of chaos theory, discovered in the latter half of the 20th century, revealed that deterministic systems can exhibit behavior that appears random, that tiny changes in initial conditions can lead to vastly different outcomes, and this sensitivity to initial conditions means that long-term prediction becomes impossible even when we know the equations perfectly. And the famous example is weather, where the flapping of a butterfly's wings in Brazil might theoretically lead to a tornado in Texas weeks later, not because the butterfly causes the tornado, but because weather systems are so sensitive to small perturbations that even tiny influences can cascade into major effects. And this has profound implications for how we understand causality in prediction and control. But chaos theory also revealed that chaotic systems often exhibit strange attractors, regions of state space toward which trajectories converge, creating patterns within the apparent randomness, fractal structures that repeat at different scales, and this suggests that even in chaos there is order. Even in unpredictability there are patterns, and perhaps the universe as a whole is like this, deterministic in principle, but unpredictable in practice. generating complexity through the interplay of order and disorder, of law and chance. And when we look at an object like 3I divided by Atlas and find patterns in its behavior, we might be seeing the signature of this deep order, the attractors in the space of possible cosmic trajectories. Ancient civilizations built monuments aligned with celestial phenomena. Stonehenge marking the summer solstice sunrise, the pyramids aligned with cardinal directions and with certain stars, Mayan temples positioned to track the movements of Venus, and these structures required sustained observation over generations, required patience and precision, required a conviction that the heavens mattered, that understanding the sky was worth tremendous effort. And we might ask what drove this obsession, why ancient peoples invested so much in astronomical knowledge. And the practical answers about calendars and agricultural timing and navigation are certainly part of it. But there seems to be something more, some spiritual or aesthetic dimension, some sense that in understanding the cosmos one was touching something sacred, participating in an order larger than human society, connecting with the eternal. And perhaps we have lost this sense in our modern world. Perhaps we have become too familiar with the sky to feel its strangeness, too confident in our models to feel its mystery. And yet every so often something comes along that reminds us how little we truly understand, how many questions remain unanswered, and 3I divided by Atlas is such a reminder, arriving from beyond and challenging us to expand our categories, to question our assumptions, to remember that the universe is under no obligation to conform to our expectations. The Voyager probes, launched in 1977, are now in interstellar space, having crossed the heliopause where the solar wind gives way to the interstellar medium, and they are still transmitting data, still sending back information about the environment beyond the sun's direct influence. And these probes carry golden records, phonograph discs with sounds and images from Earth, a message to any intelligent beings who might find them in the far future. And this message is both optimistic and melancholy. Optimistic because it assumes that such communication is possible and worthwhile. Melancholy because the chances of anyone ever finding these tiny objects in the vastness of space are infinitesimally small. And yet we sent them anyway, because the gesture matters, because the act of reaching out affirms something important about human nature, about our desire to connect, to be known, to declare that we were here and that we tried to touch the infinite. And perhaps there are other civilizations who have done similar things, who have sent their own messages into the void, and perhaps some of those messages have reached us without our recognizing them. Perhaps they take forms we have not learned to read, encoded in the chemistry of interstellar objects, or the polarization of certain wavelengths of light, or patterns in cosmic ray flux. And if we are to have any hope of detecting such messages, we must first overcome our assumptions about what a message looks like, must develop new ways of searching for meaning in the data that flows constantly through our instruments. The concept of panspermia, the idea that life or its precursors might be distributed throughout the universe by comets and asteroids and interstellar objects, was once considered fringe science, but has become more respectable as we have learned how resilient certain microorganisms can be, surviving radiation and vacuum and extreme temperatures. And we have found meteorites on Earth that came from Mars, knocked free by ancient impacts and eventually falling to our planet. And if rocks can make this journey, then perhaps microbes can too. Perhaps life on Earth originated elsewhere and was delivered here by cosmic impact. And if this is true, then life might be widespread, might be constantly seeding from one world to another. And 3I divided by Atlas, with its organic compounds, could in principle be carrying microbial life, or the chemistry that could become life under the right conditions, though the odds are overwhelmingly against anything surviving the conditions of interstellar space for the millions of years such a journey would require. But the point is not whether this particular object carries life, but whether the universe is constantly mixing its chemistry, whether the space between stars is not empty, but is traversed by countless carriers of material, Comets and asteroids and dust grains, all potentially carrying information, all potentially distributing the building blocks of complexity throughout the galaxy. There is a phenomenon in quantum mechanics called entanglement, where particles that have interacted remain correlated even when separated by vast distances, such that measuring the state of one particle instantaneously affects the state of the other. And this appears to violate the principle that information cannot travel faster than light, though careful analysis shows that it does not actually allow faster than light communication. But it suggests that the universe is more interconnected than classical physics assumed, that in some sense everything that has ever interacted remains connected, remains part of a single quantum system. And if we take this seriously, if we extrapolate this principle to cosmic scales, we arrive at the notion that the entire universe might be entangled with itself, that everything is connected to everything else through this quantum web. And while this does not give us magic or telepathy or action at a distance in any useful sense, it does suggest a kind of fundamental unity, a way in which the universe is a single coherent entity rather than a collection of separate parts, and perhaps information encoded in this quantum entanglement could in principle be accessed by sufficiently advanced technology. Perhaps the universe itself is a kind of hologram, where every part contains information about the whole. And perhaps objects like 3I divided by Atlas, having interacted with the material of another stellar system, carry entanglement relationships that encode information about their origin, and developing ways to read this information could open entirely new windows on the cosmos. The night sky that our ancestors saw was darker than anything most modern people experience, and in that darkness the stars were brilliant. Thousands of points of light scattered across the celestial sphere, and the Milky Way stretched overhead as a luminous band, and comets when they appeared were dramatic events, visible to the naked eye for weeks or months, and it is no wonder that such apparitions were considered significant, were interpreted as omens, were woven into mythology and religion. And different cultures had different stories about comets, but there was often a sense of them as travelers, as visitors from another realm, and in a sense this was correct. They are visitors. They do come from beyond the familiar, from the cold outer reaches of the solar system, or even from interstellar space. And they bring with them material that has not been processed by the heat and chemistry of the inner solar system, primitive material that preserves a record of conditions in the early solar system or in other stellar systems, and so they are messengers. Not in the sense of carrying deliberate information, but in the sense of being sources of knowledge, windows into times and places we cannot directly access, and studying them is a form of archaeology, of reconstructing past environments from the artifacts they left behind. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of active communicative civilizations in our galaxy, multiplying together factors like the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction where life actually develops, the fraction where intelligence emerges, the fraction that develops technology capable of interstellar communication, and the length of time such civilizations remain detectable. And depending on the values you plug into these factors, the result ranges from Earth being the only civilization to there being millions of technological societies in our galaxy. And we simply do not know which estimate is correct. We do not have enough data. We have a sample size of one, just ourselves. And this uncertainty is both frustrating and exciting. Frustrating because it means we cannot predict what we might find as we explore. Exciting because it means the universe might be full of surprises, and every new discovery, every exoplanet detected, every organic molecule found in space, every interstellar object studied, gives us a tiny bit more information, helps us constrain the parameters of the Drake equation, helps us understand how common or rare the conditions for life might be, and whether 3I divided by Atlas carries any biological significance or not. It contributes to this larger project of understanding our place in the cosmos, of determining whether we are alone or part of a much larger community of minds. The speed of light, approximately 300,000 kilometers per second, seems fast by human standards, but on cosmic scales, it is frustratingly slow. The nearest star to our Sun is over 4 light-years away, meaning light takes more than 4 years to make the journey. And the galaxy is about 100,000 light-years across, and the observable universe extends for about 46 billion light-years in every direction, and these distances mean that interstellar communication and travel face enormous challenges, that even sending messages requires patience on timescales longer than human civilizations typically persist, that any conversation with extraterrestrial intelligence would involve delays of years or centuries or millennia between question and answer, and this raises profound questions about whether meaningful communication is possible across such gulfs, whether we should even try, whether we should instead think about seeding the galaxy with information, launching probes or messages that will persist for millions of years, creating a kind of cosmic library that anyone could access. And perhaps other civilizations have done this. Perhaps the galaxy is full of such messages waiting to be found, encoded in durable forms, in the orbits of asteroids, in the chemistry of gas clouds, in pulsar signals, in ways we have not yet imagined. And perhaps 3I divided by Atlas, with its curious patterns, is a page from such a library, carrying information that we are only beginning to learn how to read. Mathematics is often described as the universal language, the one form of communication that any intelligent species would understand, because mathematics describes relationships and patterns that are independent of any particular culture or biology. And the idea of using mathematics to communicate with extraterrestrial intelligence goes back at least to Carl Friedrich Gauss, who suggested in the early 19th century that we could signal our presence by ploughing enormous geometric figures into the Siberian tundra, triangles and squares large enough to be visible from space, demonstrating our understanding of Euclidean geometry, and later proposals involve broadcasting the digits of pi or prime numbers, sequences that are mathematically significant and could not arise from natural random processes. And if we were to encounter a signal from another civilization, we would expect it to contain mathematical regularities, patterns that stand out from noise. And so when we find mathematical patterns in the behavior of a natural object, like 3I divided by Atlas, it triggers our pattern recognition systems, makes us wonder whether we are seeing something significant. And even if the answer is no, even if it is merely coincidence, the fact that we look, the fact that we question, is itself significant, is evidence of our readiness to find meaning. Our expectation that the universe might speak to us in the language of number and proportion. The concept of information as a physical quantity, as something that can be measured and quantified, emerged in the 20th century with the work of Clah, Buchanan, and others. An information theory revealed that information is intimately connected to entropy, that disorder and information are related concepts, and this led to profound insights about the fundamental limits of computation and communication and the nature of physical law. And one of the most striking results is the holographic principle, the idea that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. And this principle, which emerged from the study of black holes, suggests that space itself might be emergent, might arise from something more fundamental. And if we take this seriously, it means that objects like 3I divided by Atlas are not just collections of atoms moving through space, but are information structures, patterns of data encoded in physical form, and their behavior, of their trajectories, their interactions with light and gravity, all encode information that we can in principle read and decode and use to understand not just the object, but the rules that govern it, the laws of physics that shaped it, the history that produced it. The anthropic principle observes that the universe must have properties compatible with the conscious life that observes it, because if it did not, there would be no observers to note the fact. And this seems like a tautology, a trivial observation, but it has deep implications when combined with theories of multiple universes, because if there are countless universes with different physical constants and different laws, then it is not surprising that we find ourselves in one where the laws allow complexity in consciousness we could not find ourselves anywhere else, and this reasoning can be used to explain otherwise puzzling features of our universe, like why the cosmological constant has the value it does, why the fine structure constant falls in the range that allows chemistry, why gravity has the strength that allows stars to form. And critics argue that the anthropic principle is untestable, that it makes no predictions, that it is not really science, but defenders respond that it provides a framework for understanding certain otherwise inexplicable facts, and regardless of whether it is good science or philosophy, it speaks to deep questions about existence and observation and the relationship between mind and cosmos. And perhaps when we study objects like 3I divided by Atlas, we are engaging with these questions in a concrete way. We are observing the universe, observing itself. We are the means by which the cosmos comes to know its own structure and history. The idea of the universe as a computational system, as something analogous to a computer program running on the hardware of space-time, has gained traction in recent decades, with physicists and cosmologists exploring whether the laws of physics might be algorithmic, whether the evolution of the universe might be a kind of calculation, and this leads to questions about whether the universe is deterministic or stochastic, whether there is true randomness or only pseudo-randomness. Emerges NG from deterministic chaos, whether quantum mechanics represents fundamental indeterminacy or merely our ignorance of hidden variables, and these questions remain unresolved, remain areas of active research and debate. But the computational metaphor is useful because it provides ways of thinking about information and entropy and complexity, about how order emerges from disorder, about how the universe can contain pockets of increasing organization even as overall entropy increases, and if the universe is computational, then objects like 3I divided by Atlas are structures in this computation, are subroutines or data packets, are carriers of state information from one part of the system to another, and studying them is a way of reverse engineering the algorithm, of figuring out the rules of the program we are embedded in. The notion of cosmic balance, of the universe tending toward equilibrium, is encoded in thermodynamics, in the principle that entropy tends to increase, that systems evolve toward maximum disorder, toward heat death. And yet locally, the opposite happens. Local decreases in entropy are possible at the cost of greater increases elsewhere. And this is how life works, how stars work, how galaxies work. Concentrating order in one place by generating disorder in another, and the universe as a whole is in some sense exploring the space of possible configurations, sampling different arrangements of matter and energy, and most configurations are unstable, are transient, but some are self-reinforcing, are attractors, are stable, equilibria that persist, and perhaps intelligence I. It's one such attractor. Perhaps the emergence of minds that can model and predict and manipulate the environment is an inevitable outcome of complexity reaching a certain threshold, and perhaps this has happened countless times throughout the universe. Perhaps it is happening now in places we cannot see, and perhaps objects moving between stellar systems are part of a larger pattern, part of the universe's tendency towards certain states, toward configurations that maximize information or complexity or some other quantity we have not yet learned to measure. And 3I divided by Atlas might be understood in this context, not as a random chunk of matter, but as a structure that emerged from processes we are only beginning to understand. Processes that operate at scales and on timescales far beyond human experience. There is a peculiar intimacy in the study of distant objects, a connection that transcends physical proximity. And when an astronomer spends night after night gathering photons from a distant galaxy or asteroid or interstellar object, there is a relationship that develops, a familiarity, a sense of knowing this object, even though it is impossibly far away, even though no human will ever touch it or stand on its surface. And this knowing is mediated entirely through light, through electromagnetic radiation that has traveled across the void, carrying information encoded in its wavelength and intensity and polarization. And the astronomer learns to read this language, learns what different spectra mean, what absorption lines indicate what elements, what brightness variations suggest about rotation or composition or geometry. And in a sense, the astronomer becomes a translator, converting the sparse language of photons into human concepts and images and understanding. And this process of translation is always incomplete, always limited by the data available and the models we have to interpret it, but it is nonetheless real. It creates genuine knowledge. It allows us to say true things about objects we will never directly experience. And this is one of the great achievements of science, this ability to know the unknowable, to reach beyond the immediate, to construct reliable models of reality based on fragmentary evidence. The question of purpose haunts discussions of natural objects because we have inherited from our ancestors, from thousands of generations who survived by finding agency and intention in the world around them, a tendency to ask why, to assume that things happen for reasons, that events have causes that can be understood in terms of goals and desires. And science teaches us to replace this kind of thinking with mechanism, to ask not why, but how, not what is the purpose, but what is the process. And this has been immensely successful, has allowed us to understand phenomena that our ancestors could only mythologize, but it comes at a cost. It drains meaning from nature, makes the universe seem cold and mechanical. And yet perhaps there is a middle way. Perhaps we can understand that natural processes generate patterns and structures and beauty, not because they are trying to, not because they have purposes, but because the laws of physics and chemistry and mathematics naturally produce certain outcomes, and these outcomes can be appreciated aesthetically, can be experienced as meaningful, even if they are not intentional. And when we look at 3i divided by atlas and see patterns that remind us of biological or mathematical regularities, we can appreciate the beauty and strangeness without needing to invoke intention and wonder at the fact that the universe generates such structures through purely natural processes. The cosmic calendar, a popular way of visualizing the history of the universe, compresses all of cosmic history into a single year, with the Big Bang occurring at midnight on January 1st and the present moment at midnight on December 31st. And on this scale, the first stars form in late January, the Milky Way emerges in May, our solar system forms in early September, life on Earth appears in mid-September, photosynthesis evolves by early October, sexual reproduction emerges in November, multicellular life appears in mid-November. The Cambrian explosion happens on December 14th. Dinosaurs appear on Christmas Day. Humans appear in the last hour of the last day of the year. And all of recorded human history occupies the final seconds before midnight. And this perspective is both humbling and exhilarating. Humbling because it shows how recent and brief human existence has been. Exhilarating because it shows how much has happened, how much the universe has accomplished in its 13.8 billion years, and 3i divided by Atlas, having formed in another stellar system, carries its own calendar, its own history that began in the planetary disk around another star, that continued through whatever event ejected it into interstellar space, that encompasses however many millions of years it spent crossing the void between stars. And now it is here, briefly intersecting with our system, with our moment in cosmic history. And we are fortunate to be here to see it, to have the technology to detect it, to have the knowledge to understand something of what it is and where it came from. The study of asteroids and comets and interstellar objects is not just about these objects themselves, but about what they can tell us about the formation and evolution of planetary systems, about the distribution of material in the early solar system, about the processes that shape the planets and moons, about how water and organic molecules and other ingredients for life were delivered to Earth, and every object we study adds to this picture, fills in a piece of the puzzle, and over time, a coherent narrative has emerged, a story that begins with the collapse of a molecular cloud under its own gravity, that continues with the formation of a protoplanetary disk, with dust grains sticking together to form larger and larger bodies, with these planetesimals colliding and merging and being scattered by gravitational interactions, with the migration of giant planets reshaping the architecture of the system, with bombardment by comets and asteroids delivering volatiles to the inner planets, with the gradual stabilization of orbits into the configuration we see today. And this story is not unique to our solar system. We see similar processes playing out around other stars. We have detected thousands of exoplanets and characterized their orbits and in some cases their atmospheres. And each new discovery refines our understanding, helps us distinguish what is universal from what is contingent, what must happen from what merely can happen. And interstellar objects, like 3I divided by Atlas, give us glimpses of other systems, other outcomes of this process, other ways that planetary formation can unfold. The relationship between order and disorder, between structure and randomness, between information and entropy, is central to understanding how the universe wove, RKS. And one of the great insights of 20th century physics was that these concepts are not opposites, but are intimately related. That information is physical, that entropy is not just disorder, but is also a measure of information content. That the second law of thermodynamics, which says entropy always increases, is also a statement about how information spreads and dissipates, and this means that the arrow of time, the fact that we remember the past but not the future, the fact that causes precede effects, is ultimately grounded in thermodynamics, in the increase of entropy. And if we could somehow reverse entropy, if we could unmix the mixed, we would also reverse time, would find causes following effects, would remember the future instead of the past, and while this is impossible in practice, it is a useful thought experiment. Helps us understand why time has the directionality it does, why we experience it flowing in one direction, and objects like 3I divided by Atlas moving through space with their particular velocities and spins and chemical compositions are high entropy systems in some ways, disordered and chaotic, but in other ways they are low entropy, structured and coherent, and the interplay between these aspects is what makes them interesting, what makes them worth studying, because they embody both order and disorder, both information and noise, both pattern and randomness. The deep ocean trenches on Earth, the darkest places on our planet where no sunlight penetrates, where the pressure is immense and the temperature is near freezing, were once thought to be lifeful, barren zones too extreme for biology. But when scientists finally explored these depths, they found thriving ecosystems, communities of organisms adapted to conditions that seem impossible, living around hydrothermal vents that pump hot, mineral-rich water from beneath the seafloor. And these ecosystems are based not on photosynthesis, but on chemosynthesis, bacteria that extract energy from chemical reactions involving hydrogen sulfide and other compounds. And these bacteria form the base of a food web that supports worms and crustaceans and fish. And this discovery revolutionized our thinking about the limits of life, about where and how life can exist. And it suggested that life might exist in similarly extreme environments elsewhere, in the subsurface oceans of Europa, or in Enceladus, in the deep crust of Mars, in places that seem hostile but that provide the essential ingredients of water and energy and carbon. And if life can exist in such places, if biology is that flexible and adaptable, then perhaps it is more common in the universe than we previously thought. Perhaps it emerges wherever conditions are even marginally suitable. And perhaps the organic molecules found on objects like 3I divided by Atlas are not just chemical curiosities, but are precursors to biology, molecules that could, under the right circumstances, begin the long process of self-organization that leads to life. The concept of a message requires both a sender and a receiver, both an encoder and a decoder, and without both ends of this communication channel, the concept breaks down. A message that is never received is not really a message. It is just a pattern, just information that happens to exist. And yet we can imagine intermediate cases, information that was not intentionally sent, but that can nonetheless be received and decoded, that contains meaning even if no one meant it. And this is what we do when we study nature. We extract information from natural processes. We read the book of nature, as medieval scholars used to say. And the fact that this is possible, that nature is legible, that we can understand the world through systematic observation and mathematical modeling, is not obvious, is itself something that requires explanation. And perhaps the explanation is that the human mind evolved to detect patterns, to find regularities, to model the world, because organisms that could predict and control their environment survive better than those that could not. And so we are descended from a long line of pattern detectors. We are the inheritors of billions of years of evolution that selected for the ability to find meaning in chaos. And now we turn this ability to the sky, to objects like 3i divided by Atlas, and we find patterns there too. Whether or not they were intended, whether or not they constitute messages in any traditional sense, the beauty of mathematical structures, the elegance of physical laws, the harmony of musical intervals, the proportions of the golden ratio appearing in art and architecture and nature, all suggest that aesthetic principles are not merely subjective human constructs, but reflect something deep about the structure of reality. That beauty is not in the eye of the beholder, but is a property of certain mathematical relationships, certain arrangements of matter and energy, certain patterns of information. And if this is true, then the pursuit of beauty is not separate from the pursuit of truth, but is intimately connected to it. Beautiful theories are more likely to be true, not because the universe cares about our aesthetic preferences, but because beauty is a signal of deep structure, of fundamental simplicity, of elegant mathematical relationships. And when Einstein developed general relativity, he was guided in part by aesthetic considerations, by the beauty of the equations, by the elegance of describing gravity not as a force but as the curvature of space-time. And the theory turned out to be correct. Its predictions confirmed by observation after observation, and this suggests that our sense of beauty is attuned to something real, that we have learned through our engagement with mathematics and physics and music and art to recognize patterns that reflect fundamental truths about the cosmos. And when we find such patterns in objects like 3i divided by Atlas, even if we cannot fully explain them, we should pay attention, because beauty might be a guide to understanding. The ancient library of Alexandria was said to contain all the knowledge of the ancient world. Hundreds of thousands of scrolls collecting the accumulated wisdom of Greek and Egyptian and other civilizations, and its destruction, whether by fire or neglect or deliberate suppression, is one of the great tragedies of history, representing an incalculable loss of knowledge. Texts that can never be recovered. Insights that died with the scholars who held them. And we can only imagine what might have been preserved, what questions might have been answered centuries earlier if that knowledge had survived. And this reminds us of the fragility of information, of how easily it can be lost, how precious it is, how important it is to preserve and share. And in the modern age, we have built digital libraries that attempt to preserve all human knowledge, massive databases and archives that store everything from scientific papers to cat videos, and we worry about digital preservation, about whether our storage media will last, about whether future generations will be able to read our data formats, and meanwhile the universe has its own forms of preservation, information encoded in the cosmic microwave background, in the orbits of planets, in the composition of asteroids, in the layers of sedimentary rock, and these natural archives are in some ways more durable than anything humans have created, lasting for millions or billions of years. And learning to read them is like gaining access to a cosmic library, a repository of knowledge about the history and structure of the universe. And 3I divided by Atlas is a volume from this library, a book we are just beginning to open. And who knows what we will learn from reading it carefully. The practice of science is often described as objective and impersonal, as the pursuit of truth independent of human bias or desire. And there is truth to this description. Science does strive for objectivity, does attempt to minimize BI, as through careful methodology and peer review and replication. But science is also a human activity, carried out by people with hopes and fears and preconceptions. And the history of science is full of examples where bias and ideology influenced what questions were asked and what answers were accepted, where promising theories were rejected or ignored because they did not fit prevailing paradigms, where data was misinterpreted because researchers saw what they expected to see. And recognizing this does not mean abandoning the pursuit of objectivity, but rather being more careful, more aware of our own limitations and assumptions, more willing to question our own beliefs. And in the case of 3I divided by Atlas, the temptation is to see significance where there might be none, to find patterns that are really just noise, to project meaning onto an object that is simply following physical law. And yet the opposite error is also possible. To dismiss genuine anomalies as noise, to fail to see what is really there because we are too committed to existing models. And navigating between these errors requires both skepticism and openness, both rigor and imagination, both careful analysis and willingness to be surprised. The speed at which 3I divided by Atlas is traveling, roughly 30 kilometers per second relative to the Sun, is typical for interstellar objects, but is still almost incomprehensible by human standards, moving almost 100,000 kilometers per hour. And at this speed it will cross the orbit of Jupiter in a matter of months and leave the solar system entirely within a few years. And we will never see it again. It will continue on into the galaxy, perhaps eventually passing through another stellar system billions of years from now. And this transience is both frustrating and poignant. Frustrating because it limits how much we can learn, how many observations we can make. Poignant because it reminds us that the universe is vast and full of wonders, and we catch only brief glimpses of most of them. And yet even a brief glimpse can be revelatory, can change how we think, can open new questions and new lines of inquiry. And the few weeks or months we have to study 3I divided by Atlas are precious, are an opportunity that must be seized. And astronomers around the world are training their telescopes on this visitor, gathering data, sharing observations, collaborating to understand as much as possible before it is gone. The molecules that make up our bodies, the carbon and nitrogen and oxygen and phosphorus and all the others, were not present in the early universe, which consisted only of hydrogen and helium and tiny traces of lithium. And all the heavier elements were forged in stars, in the nuclear fusion reactions that power stellar cores. And when stars die, especially in supernova explosions, they scatter these elements into space, enriching the interstellar medium, and subsequent generations of stars form from this enriched material. And planets form from the debris around these stars, and eventually on at least one planet the conditions were right for these atoms to assemble into molecules and cells and organisms, and eventually into conscious beings who could wonder about their origins. And in this sense we are all made of stardust. We are the universe made conscious. We are atoms that have learned to think about atoms, and every object in the solar system, including 3I divided by Atlas, shares this heritage, is made from the ashes of dead stars, carries within its structure the history of nucleosynthesis and stellar evolution and galactic chemical enrichment. And when we study such objects, we are studying our own origins, tracing back the chain of events that led from the Big Bang to the present moment, From pure energy to elementary particles, to atoms, to molecules, to dust grains, to planets, to life, to consciousness. And this cosmic perspective is both humbling and elevating. Humbling because it shows how small we are, how brief our existence, how recent our emergence. Elevating because it shows that we are part of something vast and ancient and ongoing, that we participate in the great cosmic story, that we are not separate from the universe but are expressions of it, are ways the universe has found to know itself. The possibility that 3I divided by Atlas might be carrying a form of information that we cannot yet recognize, encoded in ways we have not imagined, is both exciting and frustrating. Exciting because it suggests that reality is richer and stranger than our current models allow. Frustrating because, if true, it means we might be missing something important, might be looking right at a message without recognizing it as such. And this is where creativity and imagination become essential to science, where we need not just to analyze data, but to think in new ways, to question our assumptions about what constitutes information and how it might be transmitted and what it might look like. And history shows that major advances often come from this kind of creative thinking, from someone asking a question that no one had thought to ask, or looking at familiar data in an unfamiliar way. And perhaps the pattern emerging from the analysis of 3I divided by Atlas is just such an opportunity. Perhaps it is calling us to expand our understanding, to develop new tools and concepts, to imagine possibilities we have not yet imagined. And even if this particular pattern turns out to be a false alarm, even if it is just coincidence or measurement error or some conventional phenomenon we have not yet properly understood, the process of investigating it will be valuable, will push us to think more carefully about what we are looking for and how we might recognize it. The loneliness of existence, the fact that as far as we know, we are the only conscious beings in the universe, or at least the only ones we have encountered, weighs on the human imagination, creates a hunger for contact, for confirmation that we are not alone. And this hunger drives programs like SETI, the search for extraterrestrial intelligence, which listens for radio signals that might indicate the presence of technological civilizations, and drives the study of exoplanets and the search for biosignatures in their atmospheres, and drives the analysis of interstellar objects like 3I divided by Atlas, because even a tiny chance that such an object might carry information from another civilization is worth investigating. And if we never find evidence of other minds, if we eventually conclude that we are indeed alone, that will be a profound discovery, one of the most important findings in history. But if we do find evidence, if we detect a signal or discover a probe or find biosignatures or decode a message that will transform everything, will fundamentally change how we understand ourselves and our place in the cosmos. And so we keep looking, keep listening, keep analyzing, keep hoping, because the question matters, because the answer, whatever it is, will be significant. The music of the spheres, the ancient Pythagorean idea that the planets in their orbits produce harmonious sounds, inaudible to human ears but nonetheless real, was based on the observation that musical harmony is mathematical, that pleasing intervals correspond to simple ratios of frequencies, and the Pythagoreans believed that the same mathematical principles governed both music and astronomy, that the cosmos was fundamentally harmonious, fundamentally ordered, fundamentally beautiful. And while we now know that planets do not literally make sounds as they orbit, we have discovered that they do indeed follow mathematical laws, that their motions can be predicted with extraordinary precision, using Newton's laws and Kepler's laws, that the solar system is indeed harmonious in a mathematical sense, with orbital resonances and relationships that reflect deep principles of physics and modern helioseismology. The study of oscillations in the sun has revealed that stars do vibrate, do have modes of oscillation that can be analyzed spectroscopically, and in a sense, this is the music of the spheres made real, acoustic waves traveling through stellar plasma. and we have learned to listen to this music, to use it to probe the internal structure of stars. And perhaps 3, I divided by Atlas, with its peculiar rotation and its Fibonacci-like periodicities, is also playing a kind of music, is also vibrating in ways that reflect mathematical principles, and learning to hear this music might teach us something profound about how the universe works, about what patterns are fundamental and which are merely accidental. The concept of emergence, the way that complex behaviors and patterns can arise from simple rules applied repeatedly, is central to understanding how the universe generates the structures we see, from the fractal patterns of galaxies on the largest scales to the intricate folding of proteins on molecular scales. And emergence means that we cannot always predict what will happen just by knowing the fundamental laws, because complexity can produce genuine novelty, can create levels of organization that have their own dynamics and their own principles. And this is why we need different sciences for different scales. Why chemistry is not just applied physics, and biology is not just applied chemistry, and psychology is not just applied biology. Because each level of organization has emergent properties that cannot be fully reduced to lower levels. And consciousness is perhaps the most dramatic example of emergence. The way that matter organized in certain ways gives rise to subjective experience, to awareness, to the sense of being a self, experiencing the world. And we have no idea how this happened, no theory that explains why consciousness exists at all. And this is sometimes called the hard problem of consciousness. And perhaps other forms of emergence that we have not yet recognized or named operate throughout the universe. Perhaps matter organized in certain ways gives rise to properties we cannot currently detect or measure. And perhaps 3, I divided by Atlas, if it does indeed embody patterns that seem almost but not quite intentional, almost but not quite designed, as an example of such emergence, is showing us a level of organization we have not previously encountered. The photographs we have of 3I divided by Atlas are not really photographs in the ordinary sense, not images formed by reflected light on photographic film or digital sensors, but are rather data visualizations, all representations of information gathered by instruments. And the object itself is far too small and far too distant to resolve as more than a point of light, even in our most powerful telescopes. And so what we see is really what we infer from changes in brightness and color over time, from spectroscopic analysis, from the way it moves against the background stars. And this inference is based on models, on our understanding of how light interacts with matter, on our theories of orbital mechanics, on our knowledge of chemistry and physics. And the models could be wrong, could be incomplete, could be missing something important. And this is always true in science. We are always working with models, with simplified representations of reality, and the models are tools, are ways of organizing our thinking and making predictions, but they are not reality itself. And sometimes, reality surprises us, behaves in ways our models did not predict. And these surprises are the most valuable moments in science, because they tell us that we need better models, that we need to expand our understanding, that reality is richer than we thought. And if 3I divided by Atlas is such a surprise, if it is genuinely anomalous in ways that current models cannot explain, then it is a gift, an opportunity to learn, a chance to glimpse something new. The idea that the universe might be trying to communicate with us, be sending messages that we need to learn to decode, sounds mystical or religious, and in some hands it certainly becomes that, becomes a kind of cosmic conspiracy theory or New Age fantasy. But there is a kernel of something legitimate here, which is that the universe is not silent, is not inert, is constantly producing information, constantly generating pattern and structure, and learning to read this information is what science does. Learning to see the signal in the noise, learning to distinguish meaningful pattern from random fluctuation, learning to ask questions that nature can answer. And in this sense, the universe is always communicating, always teaching us, and our task is to listen, to observe carefully, to think clearly, to test our ideas against evidence, to be willing to be wrong, to be willing to be surprised. And if we do this well enough, if we are patient and persistent and creative enough, we will continue to learn. We'll continue to understand more about how the universe works, what it is made of, where it came from, where it is going, and what our place in it might be. And objects like 3I divided by Atlas are opportunities for this learning, are chances to extend our knowledge, to test our theories, to see whether reality matches our expectations or whether we need to revise our understanding, and either outcome is valuable, either confirmation or surprise, either validation or correction, because both move us closer to truth, both help us build better maps of reality. The night is falling now in the observatory, and the dome is opening, and the telescope is too. Ning to track 3I divided by Atlas across the sky. And the cameras are recording, and the data is flowing, and somewhere in that stream of numbers there might be a pattern, might be something unexpected, might be a clue to mysteries we have not yet learned to ask about. And the astronomers will work through the night, will gather their precious photons, will add to the growing data set, and tomorrow, or next week, or next month, the analysts will examine the data, will run their models, will look for anomalies, will discuss and debate, and eventually publish their findings. And other researchers will read those papers and will have their own ideas and will design their own observations. And slowly, collectively, the community will build an understanding of this object, will fit it into the larger picture of solar system formation and interstellar chemistry and planetary migration and all the other processes that shape the cosmos. And most likely 3I divided by Atlas will turn out to be explicable in terms of known physics, will turn out to be unusual but not impossible, interesting but not revolutionary. And that will be fine. That will be progress. That will be one more piece of the puzzle in place. But there is always the chance, the small but real possibility, that something unexpected will emerge, that the data will not fit the models, that we will be forced to think in new ways. And this possibility, this openness to surprise, this willingness to let reality instruct us rather than forcing it into our preconceptions, is the essence of the scientific attitude. And it is what makes science not just a collection of facts, but a way of engaging with the world, a discipline of curiosity and humility and wonder. The ancient Stoic philosophers spoke of living in accordance with nature, of aligning oneself with the rational structure of the cosmos, of accepting what cannot be changed and working with the grain of reality rather than against it. And while their specific physics was wrong, based on the 4 elements and other ideas we now know to be false, there is something profound in the underlying attitude, in the recognition that we are part of nature and not separate from it, that the same principles that govern the stars govern us, that we are not exempt from natural law, but are expressions of it, and modern physics has confirmed this in ways the Stoics could not have imagined. We are made of the same particles that make up stars and planets and interstellar dust. We are subject to the same forces. We follow the same laws. Quantum mechanics and thermodynamics and relativity apply to human bodies and human minds just as they apply to everything else. And this unity, this deep continuity between us and the rest of the universe, is both grounding and inspiring. Grounding because it removes any basis for thinking we are special or privileged. Inspiring because it means that in understanding the universe we are understanding ourselves. That science is ultimately self-knowledge. That when we look through telescopes at distant objects we are looking at our own relatives, our own kin, our own kind, and 3I divided by Atlas, visitor from another stellar system, is in this sense a messenger, bringing news of family we have never met, of cousins born under different suns, and we should greet it with curiosity and respect, with the recognition that it has traveled far and has stories to tell, even if those stories are written in the language of chemistry and physics rather than words. The mathematics of symmetry, group theory, has revealed deep connections between seemingly unrelated areas of physics and symmetries. The ways that systems remain unchanged under certain transformations turn out to be intimately connected to conservation laws, to the fundamental principles that govern how energy and momentum and charge behave. And Emmy Noether proved in 1915 that every continuous symmetry corresponds to a conservation law, that symmetry in time leads to conservation of energy, symmetry in space leads to conservation of momentum, rotational symmetry leads to conservation of angular momentum, and this was a profound insight, showing that the aesthetic principle of symmetry is not just decorative, but is physically meaningful, is connected to the deepest laws of nature. And when we look for patterns in the behavior of objects like 3I divided by Atlas, we are in some sense looking for symmetries, looking for regularities, looking for conserved quantities, looking for the deep structure that underlies apparent complexity. And if we find such patterns, we have found something real, something that reflects the way the universe actually works. And even if we do not find them, even if 3I divided by Atlas turns out to be chaotic and irregular, that too tells us something, tells us about the limits of order, about how far symmetry extends, about what breaks it. The long, slow fall of 3I divided by Atlas toward the Sun, accelerating under gravity, is following a trajectory that was determined millions of years ago when it was ejected from its home system, and everything that has happened since. Every any gravitational nudge from passing stars, every photon pressure from starlight, every random collision with interstellar gas atoms has contributed to bringing it here, to this moment, to this particular path through our solar system. And there is a kind of determinism in this, a sense that the future was written in the past, that everything that happens is the inevitable consequence of what came before. And yet, there is also contingency, because tiny changes in initial conditions would have led to wildly different outcomes. 3I divided by Atlas might have passed through a different stellar system, or might have collided with something, or might have been disrupted by tidal forces, and so its arrival here is in one sense inevitable, the necessary consequence of physical law, and in another sense incredibly unlikely, the result of a specific sequence of events that might easily have gone differently. And this tension between determinism and contingency runs through all of science, through all of life. We are simultaneously free and constrained, agents making choices and particles following laws, and neither perspective is complete without the other. And perhaps 3I divided by Atlas, drifting through space following trajectories it cannot choose, illuminated by starlight it cannot escape, is a reminder of this fundamental condition, this mixture of necessity and chance that characterizes existence at every scale. The dream of interstellar travel, of humans voyaging to other star systems, has inspired science fiction for over a century. And the technical challenges are immense. The distances are so vast and the speeds required are so high, and the energy requirements are so enormous that it is not clear whether it will ever be practical, whether any civilization will ever master the technologies needed to send crewed missions to other stars. And yet we can imagine it, can design thought experiments and engineering studies, can identify what would be required even if we cannot yet achieve it. And perhaps in centuries or millennia, our descendants or our artificial intelligence successors will make such journeys, will visit the stellar neighbors, will see firsthand what we can now only observe from a distance. And perhaps when they arrive in other systems, they will find evidence of visitors from our system. Asteroids and comets that were ejected from solar orbits just as 3I divided by Atlas was ejected from its home. And perhaps these objects will be studied by astronomers in those systems the way we study 3I divided by Atlas. And perhaps they will wonder, as we wonder, whether these visitors carry messages, whether they embody patterns, whether they represent anything more than random debris. And in this way, the galaxy is constantly mixing itself, constantly exchanging material, constantly providing opportunities for observation and learning. and the universe is not static but is dynamic, is evolving, is exploring the space of possible configurations, and we are privileged to be conscious observers of this process, privileged to participate in the great project of cosmic self-understanding. The silence of the cosmos, the lack of any confirmed detection of extraterrestrial intelligence despite decades of searching, is sometimes called the Fermi paradox after the physicist Enrico Fermi, who supposedly asked, "Where is everybody?" over lunch one day in 1950. And the paradox is that given the size and age of the galaxy, if intelligence is even moderately common, then the galaxy should be teeming with civilizations, some of them millions or billions of years older than us, and we should see evidence of them, should detect their radio signals or their megastructures or their probes, and yet we see nothing, hear nothing, find no unambiguous signs of intelligence anywhere but Earth, and this silence has many possible explanations. Maybe intelligence is rare, maybe civilizations destroy themselves, maybe they choose not to communicate, maybe they transcend into forms we cannot recognize. Maybe the galaxy is too big and civilizations too sparse. Maybe we are looking in the wrong places or in the wrong ways. Maybe we are simply first. And each of these possibilities has profound implications for how we understand our place in the universe, for what we should expect from the future, for whether we are alone or merely lonely. And the arrival of 3I divided by Atlas, with its suggestive patterns, adds a tiny bit of new information to this ancient question. Suggests that if civilizations are trying to communicate, they might use methods we have not anticipated, might encode information in ways we have not imagined, might work on timescales that dwarf human lifetimes. And perhaps the right response to the Fermi paradox is not to assume that we are alone, but to keep looking, keep listening, keep analyzing, keep imagining, keep searching for the signal in the noise, because the universe is vast and we have examined only a tiny fraction of it, and premature conclusions are unwarranted when the search has barely begun. The concept of time, which seems so simple and intuitive in everyday life, becomes strange and complicated when examined closely, and physics has revealed that time is not absolute but relative, that it flows at different rates depending on velocity and gravitational field, that simultaneity is not universal but depends on reference frame, that time and space are interwoven into a four-dimensional space-time continuum. And these insights from relativity theory have been confirmed by countless experiments, by the need to correct GPS satellite clocks for relativistic effects, by observations of time dilation for particles moving at high speeds, by the detection of gravitational waves that ripple through spacetime itself. And yet, despite these successes, we still do not fully understand what time is, why it flows in one direction, whether the past still exists or has ceased to be, whether the future already exists or is yet to be determined, whether time travel is possible even in principle. And these questions connect to deep issues in physics and philosophy and touch on some of the same themes that emerge in thinking about 3I divided by Atlas, because this object carries with it a history, has a past that shaped its present, and will have a future that unfolds according to physical law, and understanding its trajectory requires understanding how past states determine future states, how information propagates forward in time, how the arrow of time emerges from the time-symmetric laws of physics, and perhaps objects like this, moving through space on deterministic trajectories, while tumbling chaotically, while outgassing unpredictably, embodies something important about how time works, about how order and disorder coexist, about how the universe balances necessity and chance. As the hours pass and the data accumulates, and the analysis continues, the astronomers working on 3I divided by Atlas are engaged in a process that is both ancient and modern, the same process of careful observation and patient analysis that has characterized astronomy since Babylonian times, but now aided by instruments and techniques that would seem like magic to earlier generations. And the conversation they are having is not just among themselves, but with the object itself. They are interrogating it with light, asking it questions in the language of spectroscopy and photometry and astrometry, and it is answering in its own way, through the photons it reflects and absorbs, through the patterns in its light curve, through its motion against the stars. And this conversation is mediated by theory, by models that translate observations into physical parameters, that turn data into knowledge, and the process is iterative, each observation suggesting new questions, each answer raising new puzzles, and slowly a picture emerges, incomplete and provisional but nonetheless real, of what this object is, where it came from, what it is made of, and perhaps whether it has anything to teach us beyond its mere physical characteristics, perhaps whether it embodies principles or patterns that we have not previously encountered. And this question, this openness to the possibility of novelty, is what keeps science vital, what prevents it from becoming mere cataloguing, what maintains the sense of exploration and discovery that drew people to science in the first place. The beauty of the night sky, the aesthetic pleasure we take in looking at stars and planets and the Milky Way and comets, is not separate from the scientific understanding of these objects, but is enhanced by it, and knowing that those points of light are other suns, some of them thousands of light years away, some of them already dead, though their light still reaches us, knowing that the planets are worlds with their own geologies and atmospheres, and perhaps even biologies, knowing that comets are icy fossils from the birth of the solar system. All of this deepens rather than diminishes the experience, adds layers of meaning and significance, connects the visual experience to vast scales of space and time, and perhaps this is the real gift of science, not just the practical benefits, though those are real and important. Not just the technological innovations, but the enrichment of human experience, the deepening of our engagement with reality, the way it allows us to see more and further and deeper, to connect what we observe to the underlying patterns and principles, to participate more fully in the cosmos by understanding it better. And when we look at 3I divided by Atlas, whether through telescopes or through the representations created from data, we are seeing not just an object but a story, not just matter but meaning, not just physics but poetry. And these aspects are not contradictory but complementary, are different ways of engaging with the same reality. The question of what it would mean for 3I divided by Atlas to be a message, to be carrying information intended for recipients like us, requires unpacking, requires clarity about terms, because in one sense everything is a message, everything carries information, everything can be read if you know the language, and in this sense 3I divided by Atlas is certainly a message, is telling us about the conditions in the stellar system where it formed, about the processes that ejected it, about the chemistry of that environment, about the trajectories that brought it here. And we are learning to read this message through spectroscopy and photometry and modeling, but in another sense, a message implies intention, implies a sender who meant to communicate something, and this is where the speculation becomes more fraught, because attributing intention requires evidence beyond mere pattern, requires demonstrating that the pattern could not have arisen through natural processes alone, and this is extremely difficult to do. Almost impossible in most cases, because nature is endlessly creative, can produce patterns of astonishing complexity and regularity through purely mechanical processes. And so, the burden of proof for claiming intentional design is very high, and rightly so, because the claim is extraordinary and requires extraordinary evidence. And yet we should not be so dogmatic that we reject the possibility entirely, should remain open to the chance that we might encounter something genuinely anomalous, something that cannot be explained by natural processes, and if we do encounter such a thing, we should be brave enough to say so, even though it would overturn many assumptions, even though it would be uncomfortable and strange. The gentle tumble of 3I divided by ATL, AS through the dark, spinning and wobbling in its complex rotation, is a kind of dance, a pattern of motion that emerged from whatever torques and impacts it experienced in its history. And this dance will continue unchanged until the object's next significant interaction. Whether that is a close approach to a star or a collision with another object or gradual erosion by interstellar particles, and for now it moves through space in a kind of eternal present, following laws that were established at the beginning of time, embodying principles that operate throughout the universe. And there is something meditative about contemplating this, about thinking of this object tumbling through space for millions of years, patient and persistent, neither hurrying nor delaying, just being what it is and going where physics takes it. And perhaps we can learn something from this. Confined in the example of 3I divided by Atlas, a kind of lesson about acceptance and endurance, about following one's path without resistance or complaint, about being what one is without pretension or apology. And while it is dangerous to anthropomorphize inanimate objects, to project human qualities onto things that have no consciousness or agency, there is nonetheless something valuable in contemplation of the non-human, in the recognition that most of reality operates without consciousness or intention and yet achieves profound complexity and beauty. And this can be both humbling and comforting. Humbling because it reminds us that we are not the center or the purpose of the universe. Comforting because it suggests that we are part of something larger and more enduring than ourselves, that the patterns and principles we embody continue beyond us, that in some sense we participate in eternity. The possibility that the cosmos itself might be tending towards something, might have directionality, might be more than just the playing out of deterministic laws or the accumulation of random events, is deeply controversial in science because it sounds teleological, sounds like it is attributing purpose to nature. And science, since the Enlightenment has generally rejected teleology, has insisted that nature does not have purposes, that things happen because of mechanical causes, not because they are aiming at some goal, and this has been productive, has cleared away a lot of confused thinking, has allowed us to understand phenomena that were previously mysterious. But perhaps the rejection of teleology has been too complete. Perhaps there are senses in which the universe does have directionality, not because some external agent is guiding it, but because certain outcomes are privileged by the laws of physics, because matter and energy naturally evolve towards certain stable configurations, because the increase of entropy is itself a kind of directionality, and life and intelligence might be examples of this, might be configurations that emerge naturally when conditions allow, might be attractors in the space of possible states. And if this is true, then the emergence of consciousness might not be an accident, but an inevitability, might be something that happens again and again throughout the universe, wherever the conditions are right. And the existence of objects like 3I divided by Atlas, carrying organic compounds through the cosmos, distributing the building blocks of complexity throughout the galaxy, might be part of this process, might be one of the mechanisms by which the universe explores the space of possibilities, by which matter learns new ways of organizing itself, by which information spreads and accumulates, and eventually perhaps becomes aware of itself. The soft glow of the telescope control room, the quiet hum of computers processing data, the occasional murmur of conversation as astronomers discuss what they are seeing, creates an atmosphere that is both technical and contemplative, both rigorous and dreamlike. And there is something appropriate about this, something fitting, because astronomy is a discipline that requires both precision and imagination, both careful measurement and bold theorizing, both skepticism and wonder. And the people who do this work are often drawn by a love of the night sky that predates any technical training, by a childhood fascination with stars and planets, by questions about existence and meaning that go beyond what can be answered by scientific method alone. And yet they channel these impulses into disciplined inquiry, into the patient accumulation of data and the careful testing of hypotheses, and in doing so they create knowledge. They push back the boundaries of ignorance, they reveal the universe to be more intricate and more surprising than anyone expected. And sometimes, in the middle of the night, when they are tired and the work is tedious and the data is noisy and the instruments are malfunctioning, they might ask themselves why they do this, what it is all for. And the answer is probably different for each person, but might include something about the deep human need to understand, to make sense of experience, to find pattern in chaos, to connect with something larger than ourselves, to participate in the ancient conversation between humanity and the cosmos. And 3, I divided by Atlas, this visitor from beyond, is an honored guest in this conversation, is bringing news from far away, is offering itself to our instruments and our questions, and we receive it with gratitude and attention, determined to learn whatever it has to teach us before it departs and is lost to the night from which it came. The story of 3, I divided by Atlas, when it is finally written, will probably not include the word message in any intentional sense, will probably explain the observed patterns as the result of natural processes, unusual perhaps, but not impossible, interesting, but not revolutionary. And this will be fine. This will be how science usually works. Anomalies get explained, mysteries get solved, strange becomes familiar. And yet, even if this happens, even if 3 I divided by Atlas turns out to be entirely explicable, it will have served a purpose, will have drawn our attention, will have made us think more carefully about how we look for patterns, what we consider significant, how we distinguish signal from noise, and it will have reminded us that the universe is full of wonders, that new objects appear regularly, that our knowledge is always incomplete and provisional, that reality has depths we have not yet plumbed, and perhaps most importantly, it will have given us practice. I will have prepared us for the day when something genuinely anomalous does appear, something that cannot be explained by conventional processes, something that requires us to expand our understanding, and when that day comes, we will be ready. We'll have the intellectual tools and the institutional frameworks and the imaginative flexibility to respond appropriately, to investigate carefully, to think clearly, to resist both premature skepticism and premature credulity, to follow the evidence wherever it leads. And this readiness, this preparedness, is itself valuable, is part of what it means to do science well, to maintain an attitude of informed curiosity, of disciplined wonder, of rigorous open-mindedness. The arc of 3 I divided by Atlas through our solar system is a parabola, a mathematical curve that emerges naturally from the inverse square law of gravity. And this curve is beautiful in its simplicity, being as an example of how complex motions can be described by elegant equations, and the fact that we can predict where this object will be weeks or months in advance. We can calculate its position to within kilometers based on a few observations and Newton's laws is a testament to the power of mathematics, to the deep connection between numerical relationships and physical reality. And when we look at the trajectory, we see not just the path of one object, but the manifestation of universal law, the same principles that keep the planets in their orbits, that determine the motion of satellites, that govern the fall of a stone. And this universality is one of the great discoveries of modern science, that the laws of physics apply everywhere, that we can trust equations derived on Earth to work in distant stellar systems, that mathematics is not provincial but cosmic, and if there are patterns in the behavior of 3 I divided by Atlas that hint at deeper mathematical relationships, if its tumbling motion embodies ratios that appear throughout nature, this is not evidence of design, but is evidence of something perhaps even more profound, which is that the universe is mathematical in its essence, that number and pattern and relationship are not human inventions, but are woven into the fabric of reality. And in discovering these patterns, we are not imposing order on chaos, but are finding the order that was always already there, waiting to be noticed, waiting to be appreciated. As the story draws to a close, as 3 I divided by Atlas continues its journey outward from the sun, beginning the long climb back toward the outer darkness, we are left with questions rather than answers, with wonder rather than certainty. And perhaps this is appropriate. Perhaps this is how it should be. Because the universe is not a puzzle to be solved once and for all, but is an ongoing mystery to be engaged with, to be explored, to be experienced. And each new discovery, each new observation, each new object, like 3I divided by Atlas, adds to the richness of our engagement, deepens our appreciation, extends our understanding while simultaneously revealing how much remains unknown. And this is not frustrating, but is exhilarating, is what keeps science vital, what makes it an adventure rather than a catalogue, what transforms it from mere fact-gathering into a grand human enterprise, a collective effort spanning generations and cultures to understand our cosmic context, to map the universe we inhabit, to trace our origins back to the Big Bang and forward to whatever future awaits. And in this enterprise, objects like 3I divided by Atlas are not just data points, but our fellow travelers, our companions on the journey, our voices in the conversation, and we listen to them with attention and respect, knowing that they have come from far away and have much to tell us, knowing that every photon they reflect carries information, knowing that in studying them we are studying ourselves, are exploring the conditions that made our existence possible, are investigating the cosmic heritage we share with all matter every YW, air. And as the observations wind down, as the object grows fainter and harder to track, as it recedes into the outer solar system and eventually beyond our ability to detect, we say farewell to this visitor. Thank it for what it has taught us. Remember it as we would remember a wise teacher or a patient guide, and turn our attention to the next mystery, to the next object that will appear in our telescopes, to the next question that will arise from our data, to the next chapter in the eternal story of humanity's attempt to understand the cosmos, knowing that the story never ends, that there will always be more to learn, more to discover, more to wonder at, and feeling grateful to be alive at this moment in cosmic history, to have the technology and the knowledge and the curiosity to engage with questions that our ancestors could only dream about, to participate in the great project of cosmic self-understanding. And as the night deepens and the telescope continues its patient watch and the data streams flow and the universe reveals itself one photon at a time, we drift into a kind of cosmic sleep ourselves, a meditation on deep time and vast space and the patterns that connect all things, feeling ourselves part of this great pattern, this vast tapestry, this cosmic dance, and finding in this recognition not loneliness but connection, not insignificance but meaning, not fear but peace. And so we rest, cradled in the arms of the cosmos that made us, surrounded by mysteries that will keep scientists awake for generations to come. But for now, for this moment, letting ourselves sink into the deep quiet between the stars, where something moves with purpose, carrying not destruction but the universe's oldest song, harmony and pattern and balance, cosmic mathematics singing itself across the light years, and we listen, and we learn, and we sleep, and we dream of what is yet to come.